Hi, this is my first programming tutorial ever, and in this video I will show you how to obtain a smooth curve from any sequence of 3D or 2D coordinates. This is an easy programming tutorial you could do to learn programming and also produce an actually useful program. Here I'm showing the backbone of a protein structure, which consists of repeating units of a nitrogen in blue and two carbons in purple. The goal of this tutorial is to obtain this smooth white path, which quite precisely reproduces this cartoon loop representation of this molecular viewer called PyMol. I didn't look up the source as to how this program obtains this path, but I'm going to show you an easy way there. It might look otherwise, but actually this path is ignoring all but every third atom, which is the alpha carbon. So, in short, we start with this angular path of alpha carbons with any number of middle points inserted and smoothen it. During smoothening, the given points are fixed, while every point tries to straighten the angle with its neighbors. Each point also pulls neighbors together so that because of the balance of the forces, they will not stick together but maintain a regular interval. Now I'll tell you how all this can be implemented. We'll do something like a physical simulation where particles move through time, changing locations, velocities, and forces. In such a simulation, time is described as small discrete units. In each tick of time, forces are calculated, and velocities and locations are updated. But we are performing a type of optimization where rolling down the penalty function is enough. Having velocities can help jump escaping local minima, but in this case, we do not need to worry about them. While often in physical simulations, forces are generated from all-to-all interactions of particles, here we only install springs where we need. I've come up with three types of springs that care about lengths and angles. Each take 2, 3, or 4 points and exert forces on them to drive the lengths and angles toward an optimal value. We do not care about dihedral angles here. The essential one is the angle spring, and length spring is there to make sure that things are in order. The working of a length spring is the simplest. To reduce its length, it exerts forces to drive them toward each other or into the middle point, and the force is scaled by the amount of excess length. That of an angle spring is more complex. To conserve the length of the sides, we must add a vector that is perpendicular to the sides, which in 3D can be determined in terms of the outer product of each side with the outer product of the sides. Ambiguity arises when you have zero or straight angles, but if you have to break off from them, for example, from straight to smaller angles, you may have to nudge it in a random direction. Now, here is an awkward point which I realized while creating these slides. The original design of the angle spring was in a sense flawed. For instance, if a series of points are an arc and the ideal angles are straight, the way the springs should move the points is into a straight line. But since the angles themselves are facing the concave face, the angle springs inflate the arc into a larger loop. To counteract this takes much stronger length springs, which would create actual straightening effect, which would truly drive the angles toward the optimum. Due to the weird design, my first design required the user to determine a balancing coefficient which would allow the user to pick from a range of paths from straight to smooth to loopy and to loopy. Well, such arbitrary paths may have their own use, but for our original purpose of obtaining the optimal smooth path, the angle springs needed to be redefined. The answer was to exert forces on the middle points too. Furthermore, setting the forces on the inner vertices so that the sum would equal 0, made these springs exceedingly more useful for my other purposes. To use the new angle spring, I only had to set the length springs to be very weak, and the optimal paths were virtually identical. Thank you for listening, and I will give you the sources unless it is for commercial purposes.